Groundwater Hydraulics Project 3. I'm Michelle Sutherland.
I'm Rachel.
I'm Chris.
I'm Jack.
The site we're looking at is an inactive landfill where a lot of harmful chemicals and contaminants have been dumped over many years. There is a sand and silt aquifer that underlays the site with a thickness of 140 feet. A low conductivity clay lies below the aquifer. The existing site has a hydraulic conductivity of 43 feet per day, recharge of 0.005 feet per day, and porosity of 0.1. The goal is to keep contaminated landfill water out of the river. We'll do this by trying different remediation strategies and alternatives. The goal is to reduce particle flow from the landfill to the river, decrease travel time of particles, and reduce cost to best of our ability.
So, alternative A is our base case for the landfill in its current configuration. And so what we did in order to track kind of where the water from the landfill is going is by adding particles to the landfill. So using ModPath, we digitized the outline of the landfill, which added a particle to each cell. And then as you can see, once the model was run, all of the particles currently are going towards the river with a particle travel time of about 26.2 years. And then the flow of the river currently without any influence to the landfill is about 44,000 cubic feet per day. So for alternative B, which is our first alternative, we decided to try an impermeable cap over the landfill area. And basically what that was just a cap that prevented recharge to the area, which decreased the flow from the landfill to the river. And so you can see that by the increase in the particle travel time with also a decrease in the flow of the river because there was less flow coming from the landfill. The only issue with this is that, as you can see, all of the particles still reach the river, and so we did not achieve our goal with just the cap.
So in alternative C, we use the same impermeable cap as the previous alternative, but this time we added a confining wall with a hydraulic conductivity of 0.001 feet per day, and it had a porosity of 0.1. So this confining wall did help with the time it took for the particles to contaminate the river. It took 61 years for the particles to go from the landfill into the river, but still, they still reached the river eventually, and so this needed to be addressed before it could be considered an alternative to remediate the site. We tried to see if changing the porosity of the confining wall would help with remediating the site, but so we reduced it to half of the original porosity at 0.05, and this did the opposite of help because it actually caused the particles to reach the river in half the amount of time that it did when the porosity was 0.1. And so this did not help to remediate the site.
So alternative D was to have the impermeable cap, the slurry wall as we've had, and then add 14 drains along the southwest corner of the landfill in the direction the particles are already flowing. And so we set the hydraulic conductivity of the drains to 10 feet per day. And as you can see, all the particles were captured by the drains, which was great. So we kind of achieved that with this alternative. However, the flow of the river greatly decreased, and the flow of the drains with about 5,000 cubic feet per day was much higher than anticipated, and all that water has to be treated before it can go to the river or as an effluent. The particle travel time also increased to about 59 years, and so it took a lot longer for the particles to go from the landfill to the drains than expected. The drains were also set at a stage 40 feet below the top elevation, so they're set at 100 feet of elevation.
In alternative F, we decided that alternative D worked fairly well, but we wanted to make a couple changes to those drains. So we actually removed 3 of the 14 drains. So we now have 11 drains, as you can see in this model picture. So we removed 2 drains on the east side and then 1 drain on the west side. These drains have the same depth and stage below the top elevation, so they're all located at 100 feet. And instead of a hydraulic conductivity of 10 feet per day, these drains have a hydraulic conductivity of 5 feet per day. We made these changes to better cut on some cost and still see if we can model it the same without any of the particles going into the river. So as you can see, we were able to do that, and no particles go into the river with these changes in hydraulic conductivity and number of drains. As you can see, the flow to the drain, these drains capture about 500 cubic feet per day less than alternative D, which makes sense considering these change of characteristics. And another big drastic change is the particle travel time. In alternative F, this travel time is almost 13 years, where in alternative D, it was almost 60 years. In alternative E, this is our final design. We decided on going on this design, which has a well just on the southeast side, just right by the landfill. This well will have a pumping rate of 1,600 cubic feet per day. This model also is modeling the impermeable cap and the confining wall with no drains. As you can see from alternative F, there are no drains. So with this alternative, the flow to the river is about 1,000 cubic feet per day more, and has the lowest particle travel time in years than any other model that we've seen, which is another attractive characteristic about this model. So we see in this model that no particles go into the river. It's all constrained within that within the confining wall here. And in this model, we tried a few different things with the well. We tried placing it right outside of the confining wall. We tried different combinations with placement and flow rates. We placed it inside the landfill, and we decided on this one cell where we have the well here in the blue square that you can see on the model. That represents the well, and this is the placement and combination with a 1,600 cubic feet per day flow rate that we found to be the best for this model.
So our final recommendation is to choose alternative E because it does prevent the particles from entering the river, but it's more cost effective than alternative F because less water needs to be treated than if a drain was used instead of the well. The well captured 1,600 cubic feet per day, and the drains collected over 4,000 cubic feet per day, and all of that water needs to be treated, and that's expensive. And so it would be more cost effective to implement a well rather than the drains. Also, the well collected the particles 4 years faster than the drains did, and so that would mean that the site is going to get cleaned up faster. And so on all levels, this is clearly the better alternative for putting in the site.
So one of the pieces of data that we collected throughout all the alternatives was the particle travel time. This is one of the things we wanted to monitor as we were doing the different alternatives. And so looking at alternative A as our base case of 26.2 years, we can see where the impermeable cap and the wall added significant time to the particle travel, where once we added the well and the drains, the travel time definitely decreased. So as you can see, E has the lowest particle travel time, which gives us the shortest time from leaving the landfill to being captured, and that was what we were looking for. Mass balance of flows was another thing that we wanted to consider while running through alternatives. Again, in alternative A, you can see the river was about 44,000 cubic feet per day. And so you can see every alternative definitely decreased it, especially adding the confining wall. However, in order to maintain that no particles got to the river from the landfill, this was necessary. And so in alternative E, this was with the well, as we discussed previously, was the only time that all the particles were captured, and it still had the highest outflows to the river. And so that was another deciding factor.
To conclude, we wanted to go over some lessons that we had learned going throughout this process. First, we wanted to touch on the effectiveness of our final design, the alternative E, with the pumping well of 1,600 cubic feet per day. We think that this is a very effective design because it does capture all the particles, as Chris had mentioned, and it does so in a fashion where it doesn't take a very, very long time for the particles to travel to the well, and it does so in a cost-effective way, as Rachel had mentioned earlier. Another thing that we had learned is that we could have tested a little bit more variations of the drains. Like we had done in alternative D and F, we had changed the drains and got rid of 3 of them, changed the hydraulic connectivity of them. But another things we could have messed with are just messing with the number of drains as well as the stage. and the hydraulic connectivity as well. We could have messed with those and seen where we could have gotten better results with using drains. All in all, we learned that multiple ways are possible to be able to get the same goal here and reduce flow from the landfill to the river. There's multiple different strategies and things to use to improve the site and make sure that the water isn't going to the river. So that's all we got. So thank you all for listening.